Hi, welcome back to my channel, and for today's video, we will be talking about the linear transformation. So before we start, I would like to thank everyone for those who had been supporting me for a very long time. Thank you so much. And for those who are new to my channel, please don't forget to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon. Okay, so on the start of exploring about the ideas of linear transformation, there are things that we have to examine first. Let's say, for example, we have to consider a column vectors, let's say fn, this one, raised to n plus times 1. And we have to consider a row vector that's f to the 1 by n. And then we also have to consider an n tuple vector. Okay, so observe that these are vectors. This one, this f raised to n by 1 and the f raised to 1 by n and the f raised to n are actually vectors. However, they're not of the same vector spaces, although they behave on the same way. Why? If you would like to reconsider here, a column vector, if you add that by another column vector here, let's say this one, that means you're actually adding two column vectors. This is the same way as we add with a row vector. I'm sorry. Okay, let's assume that's there's a space there, and that's the same as when we add an n-tuple vector. Let's say that's it. Okay, so observe that they're not actually on the same vector spaces, but they actually behave on the same way because these three spaces are what we call the isomorphic vector spaces. So in math, when we talk about isomorphism, we often referred or treat these vector spaces as one and are the same. That's it. But before talking about the isomorphic vector spaces, we will have to start first with the concept of the linear transformation as what is the point of our video here. Okay, so let's start with a formal definition here. So the function f from v to w is a linear transformation. Okay. Whenever both of the following properties are satisfied. So what are these properties? Number one, this one here, okay, this one will hold for all v1 and v2 in V. Okay. And number two, this one here hold for all R in V and for all V, of course, in V. By the way, your R here, sorry, should be on the field F because these V and W are actually vector spaces over a field F. That's it. Recall that on your basic study of elementary functions, this one here is actually a domain. So this is the same with the linear transformation. This one here is actually the domain of your F, and this one here is actually the codomain. Okay. In the event that your V here is equal to W, so that is, you have F equals V to V, then this linear transformation now is called linear operator. That's it. Okay, so let's consider an example here. The example is, suppose we have a function here f from v to w, and we define such mapping as v sending to zero vector in W. So we denote that as 0 sub W. That means it's the zero vector from W. So if you notice, this is actually a linear transformation in the sense that it satisfies the definition. So let's double check. So let V1 and V2 from V. So if you double check here, that's f of V1 plus V2. This is okay. We would have zero vector. And remember that zero vector, I can have this as zero. The sum of two zero vectors are actually zero. So that means I can split that zero into two zeros. And then I would have this one. So that means condition 1 is satisfied. Also, so for any vector in V, if you double check that with a scalar, let's say our scalar here is a alpha. So you have alpha V. Remember that the alpha V is one vector entirely, so I would get zero vector, and then I would get alpha as well. So that's exactly alpha times f of V. So therefore, this function here is actually a linear transformation. In fact, we call this as zero linear transformation. That's it. Okay, so another example is we have the function, we have the mapping, this one, which maps from V to V, and this is actually sending V to itself. That's V. So in fact, this is actually a linear transformation, as you can check. If you have any clarification for this, you can comment down there. But it's obviously a linear transformation, and it's obviously a linear operator in the sense that the domain and the codomain are equal. Prominently, this linear operator is actually an identity linear operator. That's it. Okay, so another example. So let M be an R. So that means our field here is the set of real numbers. So is the function maps from R to R, sending X to MX, a linear transformation? So we will find this out here. Okay, so to check on that, let x1 and x2 in R. So we have f of x1, fm of x1 plus x2. So what's the definition again? This is equal to m times x1 plus x2. So that's the definition of the mapping given on this example. And then I can distribute so that I'd have mx1, mx2. This is actually f of x1. And this one here is actually f of x2. So condition 1 here is satisfied. Okay, so let's consider x in general as element of R. And in this case, we would introduce another scalar here coming from R, such that if we have to evaluate this one, remember that this is the same as M. By definition, that's M AX. Okay, so remember that M here is in R and A here is in R, and associativity and the commutativity at the same time holds in R. So we could have A mx here. And so this is equivalent to A times this mx is actually f of x. So therefore condition 2 is satisfied, which implies that this one here is a linear transformation. That's it. Okay, so let's consider another example here. The function, in this case that's d, maps from r sub n of t to the same r sub n of t, and it's defined as the polynomial p of t sending to its derivative. So this mapping actually says that if you have a polynomial, the output of the function is actually its derivative. So we will show whether this mapping is actually a linear transformation or not. Okay, so to show on this, let us consider two polynomials here, the p1 of t and p2 of t. So they're actually element of r sub n of t. Okay, so that's r sub n square bracket t. Okay, now observe that if I'm gonna take the d of p1 of t plus p sub 2 of t, that's actually the derivative of the sum here. And it's already defined in our basic calculus here that the derivative of the sum is actually the sum of the derivative. So I would get this one. So this is pretty obvious because it's actually explained in the basic calculus that when we take the derivative of the polynomial, like the sum of two polynomials, it's actually getting the sum of the derivative of two polynomials. So basically, the condition 1 here is already proven. Now let's double check on the condition 2. Now, we'll consider A here to be an element of the field. Our field here is R. So let's consider P of T. That's an element of the polynomial. That's R sub n of T. And then if you take the D of A, P of T rather. So by definition, this is the same as taking the derivative of this. If you take the derivative of a polynomial with a given coefficient, it's technically taking out of the coefficient and then take the derivative. That's a chain rule. And that's it. So technically, the condition 2 here is actually satisfied. So therefore, this function here is actually a linear transformation. Okay, so let's consider another example here. Let's consider a function. So a function maps from f sub n of t, so that's a polynomial, mapping to f sub n of t, square bracket t rather. So we define this in this way. If p here is actually a polynomial of the form a sub 0 plus a1 t plus up until you have an to the tn, then your f of p is actually this one here, a sub n plus a sub n minus 1 of t plus up until you have a sub 0 of t to the n. So that will be the definition of your mapping from f sub n square bracket t to f sub n square bracket t. Then we will have to show that f here is a linear transformation. So let's double check if that will work to be a linear transformation. So let p be this one. And let q be this one. So to show that condition 1 is satisfied, so we will have to show that f of p plus q. So our goal here is f of p plus q here. We can simply extract that to f of p plus f of q. So technically this is the same as f of your p here is a sub 0 plus a1 t plus up until an to the tn. And then I can add that by the q, by the part of q, that's b sub 0 plus b1t plus up until bn to the tn. Okay? Now, observe that I can write this in this way. A sub 0 plus B sub 0. So that means I group them according to their subscripts. So A sub 0, B sub 0, plus I'd also have A1 plus B1, and that's T, plus up until you have AN plus BN, that's T to the N. Okay. Now, so via definition of our given mapping here, so I can have, what's the definition again of our mapping? The AN plus BN doesn't have a variable because it's t raised to 0. So that means I would have AN plus BN here plus, and I would get AN minus 1 plus BN minus 1. And that's T. And then up until you'll get A sub 0 plus B sub 0 times T. So, and then you get this result. So I can regroup them again in the way that I would have AN and then AN minus 1 T up until I would have A sub 0 T to the N. Okay, T to the N here. And I will also have a group of Bn plus Bn minus 1 T up until B sub 0 T to the N. Okay, now remember this is already our f of P. And this one here is actually our f of Q. Okay, so therefore the condition 1 is satisfied. So our next problem is to identify the condition 2, whether it's satisfied or not. And then before we can jump into conclusion that whether this mapping is actually a linear transformation or not. Okay, so let us consider the R here. So our R here is coming from F. The capital F, the field, I mean. So evaluating on f of Rp here, this is actually the same as f of R, and that would be A sub 0 plus R, A1B, I'm sorry, A1T, plus up until R, AN to the times T to the N. Now, by definition, R here is just a coefficient, so nothing will be changed with that. So I would get RAN plus, I would also have RAN minus 1T plus up until R A sub 0 T to the N. Okay, now R here is just part of a field, so I can extract R out from this polynomial. So I get R times AN plus AN minus 1 T plus up until A sub 0 T to the N. So R here, this is already our f of P. So therefore, condition 2 is satisfied, which implies that the mapping of this form is actually a linear transformation. Okay, so let's consider an example here. So let's consider a mapping. So the function R to R here, R squared to R squared rather, that's defined as sending a pair AB to a pair A0. So this is actually a mapping which projects all vectors to the x-axis. So which means that if you have an xy plane here, so if you find a vector here, you are actually projecting a point of reflection from this point here corresponding to a point on the x-axis. So we will check if f here is linear transformation. Okay, so let's consider points A sub 1, B sub 1, and I will also have A sub 2, B sub 2 to be elements of R2. So let's consider two vectors here. Now, I would check if this will work. Sorry. So that should be A1, B1 plus the point A2, B2. So technically, this is the same as f of a1 plus a2, comma b1 plus b2. Okay, so by definition, this is actually the point a1 plus a2, and that's 0. And then I can split this point here to be a1, 0 plus a2, 0. Now, the point a1, 0 is actually the output when we input a vector to the f. That's actually a1, b1, plus I also have f of a2, b2. So therefore, condition 1 here is already satisfied. Okay, so let's consider a scalar. Let's say a scalar r here coming from r. So if we have to evaluate r, a1, b1, so basically this is f of ra1, rb1. For convenience, I won't use the subscript anymore because we're only using one vector here. So I'm gonna delete the such subscript. Okay. So this is actually RA0 by definition. That means the second coordinate is actually 0. And simply I can extract R here. I can extract R here, and that will be A0. And so the point A0 is actually the output of our when we input the AB point. So that means that's actually f of AB. Therefore, condition 2 is satisfied, which implies that this mapping here is actually a linear transformation. That's it. Okay, so let's consider an example here. We define a function from R squared to R3, and we define this in this way. And that will be A1 plus A2, A2, and that's A1 minus A2. Okay, so is this linear transformation? Okay, so I want you to solve this or prove this, whether this function maps from R2 to R3 defined in this way is whether a linear transformation or not. So if you have any questions or clarification, you can comment down there so that I would know. And you could also post your answer whether it's a linear transformation or not. And then we will check that. Or you can message me and on how to show that this is a linear transformation. So I'm not going to show here whether it's a linear transformation or not because I want you to do it on your own. Okay? Okay, so we have another example here. Let's say a function maps from R to R. And in this case, we defined the x sending to e to the x. So we will show that this mapping f here is a linear transformation or not. Now observe that in showing that a given function here is a linear transformation, you just have to satisfy with the two conditions. First is when you take the sum there inside, you actually end up having the sum of both f there. And then the second is the scalar. You can take it out from the inside. Now, to show that the function is not a linear transformation, you just have to get at least one of the conditions that would contradict with a given statement. So example here, this function here is not a linear transformation. Now, to show that this function here is not a linear transformation, we would only have to consider one condition that would fail. And then it won't matter if whether the other conditions might fail or not. Okay, now note that the elements here, 0 and 1, are elements of R here. So observe that f of 0 plus 1 is actually f of 1. And f of 1 here, as by definition, that's actually e to the 1 or e. But remember, e is not equal to e plus 1 plus e. Because 1 plus e is the same as f of 0 plus f of 1. F of 0 is 1. F of 1 is actually E, and it's not equal to this here. Therefore, condition 1 is not satisfied, and so this is not a linear transformation. Also, a function maps from R to R here, sending x to the absolute value of x. So observe that if we consider elements x and y here from R, and then if I'm gonna solve f of x plus f of y here, that is the same as the absolute value of x plus the absolute value of y. And technically, this is actually greater than the absolute value of x plus y, and that the absolute value of x plus y is the same as f of x plus y. In this case, your x plus and y here are coming from R, and the product of x, y here is less than 0. Meaning to say that one of these, either x or y here, is negative. That's it. So, which means condition 1 fails to hold, and so this is not a linear transformation. Okay, so we will consider another example here. The function from R to R, and in this case, it's sending x to x cubed. So we will check if this is a linear transformation or not, which is obviously not a linear transformation. Why? I'm gonna use a different color. So here, if you consider x and y here to be element of your R, now f of x plus y, that's actually the output there is x plus y quantity cube, right? By definition of this mapping. Obviously, this is not equal to x cubed plus y cubed. Your x cubed plus y cubed is actually f of x plus y f of y. This is not equal in the sense that we're working on R, where we're not working on a different group modulo 3 or whatever. We're only working this on R. So therefore, this is not a linear transformation. That's it. Okay, so taking a quicker look back on the mapping here, this map here from R to R defined by sending x to e to the x. Now, we have shown that this is not a linear transformation. However, the thing is, we can change the underlying vector space to make it a linear transformation. Now, in this case, we will assume that our V here contains x in R such that your x is greater than 0. Okay. And we define operations. So define plus and dot here in V as this. For all x and y in R, and A in R, we have these operations defined here. So here in this case, the plus here is actually the usual multiplication. So this is the usual multiplication, and this product here is the exponentiation. Okay, so this is now the new definition of our mapping here. So in that case, going back to this thing here, by this definition here, if we have to evaluate x and y, x plus y rather, that's the same as e to the x plus y. Okay, now this is the same as e to the x, e to the y. And so since this is actually a product of two things, that's the same as the sum of two things. So technically this is f of x plus f of y. In this case, condition 1 is already satisfied. Now, for every r in R, okay, so f of r x, that's the same as e to the rx. Okay, and this is the same as e to the x times r And remember, by the definition of exponentiation, this is r e to the x, which is equal to r f of x. Okay, so that's all for now. So thank you so much for watching. So we will continue with this video for linear transformation because we have not been able to finish yet on this linear transformation. We have only introduced different examples for such linear transformation. We have discussed its intuitive idea for this linear transformation. Thank you so much for watching. So if you have any questions or clarification, please don't forget to comment down there so that I would know and we will discuss it thoroughly. And for those who are new to my channel, please don't forget to subscribe so that you'll be updated on a lot of videos and for the continuation of this video here. And for those who have been here for a very long time, again, thank you so much for your undying support. So thank you so much, guys, and have a great day. Bye for now.